Hello, welcome back. This is Kinematics problem number 3. I'm going to look at this traffic light scenario. Now, some of my numbers didn't actually copy over, so I'm going to take a second to kind of write those in. Okay, so a person is driving their car at, this is going to be 45, this goes right there, kilometers per hour, just like that, and approaches an intersection just as the traffic light turns yellow. She knows that the yellow lasts for 2 seconds before turning red, and she's 28 meters away from the near side of the intersection. Should she try to stop, or should she speed up across the intersection before the light turns red? The intersection is 15 meters wide. Her car's maximum deceleration is negative 5.8 meters per second squared. Whereas it can accelerate from 45, so its original speed, to 65 kilometers per hour in 6 seconds. Ignore. Alright, so I'm going to draw a visual of what this problem is. So what you have is a car. There it is. This already has its motion, which is 45 kilometers per hour. As such, and it is 28 meters away from the intersection. So I'll draw a traffic light. Why not? This is the traffic light. Lovely traffic light. There it goes. We know that this intersection is 15 meters wide. Like that. And then the question is, what should they do? Should they speed up or they should slow down? Now, the light, let's see what our information is. She knows that the light lasts only 2 seconds before turning red. So basically at this point, she has 2 seconds to get across basically this, or more or less. What I'm going to figure out is how long it takes for that person to cover this distance and compare it to the 2 seconds. Where are you at 2 seconds? If we know where they are at 2 seconds, distance-wise, then we can figure out where the car is, and then we can kind of decide whether or not they should speed up or slow down. So with that said, and also right here, we're going to be applying the brakes. So I'm going to figure out, starting at this speed, how far that person goes. Also, something else we need to look into is the fact that we have two things here. We have a deceleration and an acceleration. So its deceleration is 5.8 meters per second. So that's how quickly this person can stop. We are also given how quickly the person can go faster or accelerate. Now, they don't give us the acceleration, but we could actually figure out pretty quickly by using acceleration is velocity final minus initial over time. And why don't we just, let's do that first, just to get a picture of what's going on. So the final velocity is 65 kilometers per hour. Actually, let's, I changed my mind. Before we do this, let's get, these kilometers per hour into meters per second. Let's just do that right away. I'm going to kind of do that up here on the side right here. So with that said, I'm going to do 45 kilometers per hour times in 1 hour. There's 3,600 seconds, so I'm just doing our basic conversions. Times in 1 kilometer, I'm doing 1,000 meters. So that should give us meters per second. Good. So when we do that, 45 times 1,000 divided by 3,600, what we get here is 12.5 exactly meters per second. So that's going to replace that. I like to do that because exactly what I just did, because sometimes I get confused. So I don't want that number, I want this number. And then the 65, so this is also the 12, so just cross that out. I'm going to convert this right away. I'm going to use the same method. So what's going to happen is I'm going to do 65 times 1,000 divided by 3,600. Let's do that. I get 18.06. I'm rounding here, 18.06 meters per second, just like that. Okay. So now that we have our two velocities, we can find acceleration. Here we go. My acceleration is the final, which is the 18.06 meters per second minus 12.5 meters per second divided by 6 seconds. Here we go. And doing that, 18.06 minus 12.5 divided by 6, 0.93. I'm going to round that up. Meters per second squared. So already you can see that the speeding up versus slowing down, right? The speeding up, the acceleration is much slower than it is, slowing down. So I'm going to take, I'm actually solve both of them with the both different accelerations just to kind of show you where this will go. So like I said, I want to figure out where we are at 2 seconds, because if we're before the light at 2 seconds versus at after the light at 2 seconds, it's going to kind of tell us if we need to speed up or slow down for the most part, or try to stop or speed up. So let's do both. So technically, in order for the person, well, like I said, let's figure out where we are at 2 seconds using those two accelerations. So let's start with slowing down. What if we slow down? So where are we at 2 seconds? Now, and that's a where, so we're looking for a distance or an x. Now, of course, you could solve these any way you'd like. There's more than one way to solve this, but this is how I'm going to solve it. So let's try the slow down. Our information is the following. Our initial velocity for slowing down is 12.5 meters per second. Our final velocity, if we come to a stop, will be 0. The time we have to do this, let's see. Actually, I'm going to take a step back here and even just say, where are we? So without the time. Let's see where we are. If we start right here and stop, how far did we go? Because we are fixed with this acceleration right here. Now I'm using a deceleration, just like this, 5.8. So where are we? I don't even need the time. Let's figure out where we are. So I'm going to use this equation. V squared equals VI squared plus 2A delta x. So here we go. This is 0. This is going to be our initial velocity. To negative 5.81 meters per second squared delta x. So where are we when we try to stop? So let's see. I'm going to use quick algebra here and solve for delta x. So first I move the 12.5 squared. That's going to move over. Divide by 2, divide by 5.81, or just 5.8. So in order for us to come to a complete stop, 13.47 meters. This is a complete stop. Oops. Complete stop. So notice that this information tells us that from this point, if we go 13, which is roughly a little less than half, so about here, from here to here, we'd be at v equals 0. In other words, we can obviously try to slow down. I think that is the best method because we're not crossing the intersection. It looks like this person has plenty of time to do that. How long does it take to, stop? Let's see. We could do that too. We could do this one to figure that out. VI plus AT. See how long it takes to stop, so it's going to be 0 here. This will be the 12. 5.8 negative. I'm leaving out the units because I'm just running out of space. Times t. So solving for that, so 12.5 divided by 5.8 will give us, it'll take us 2.1 seconds to stop. So what does that mean is it'll take us 2 seconds to stop about right here, and we'll be in front of the red light, which is, what we want. So far, I'm going to say that this is the case. We want to slow down. I kind of saw that in advance because this is way faster than trying to speed up, which is a pretty, valid, problem and everyday type of thing. This is generally good practice, right? Slow down before speeding up. But let's just, kind of humor the idea of speeding up. So I'm actually going to go down. So technically we want to slow down. That's the official answer, slow down. Let's speed up. Let's do the same method. Let's speed up from the initial velocity. And let's say that our acceleration is 0.93 meters per second squared. And then let's do this. We're going to figure out where we are. We're going to, again, figure out our delta x. And not only that, but where we are at 2 seconds, like we said before. So I'm going to use delta x is equal to VIT plus 1/2 AT squared. So I'll tell you exactly where I am at 2 seconds with that acceleration, with that velocity. So here's what it looks like. So our initial velocity is 12.5, so we don't need a final velocity. Technically, we don't know what we speed up to anyway, so we can't really assume that we went to the 18. Let's do this. The 0.93 times 2 seconds. There we go. So I'm going to do the first part, 12.5 times 2. That gives me 25. Then I'm going to add that to the next part, so 0.5 times 0.93 times 2. That should be squared. Squared. Go. So what we get is delta x is 26.86 meters. So speeding up. Let's take a look where that puts us. Uh-oh. Speeding up puts us right here. This is 28, so to scale, like 26 is like right here. And at this point, the light has turned red. So, I mean, what we're doing is basically at this point, we have crossed, the intersection while the light was red. This is very dangerous. So, obviously, we're not stopping here. We actually got to our max speed here. So even worse, we're speeding across this. So we say no to speeding up. We're not going to speed up. No speed up. And we're going to say yes to slow down. Slow down is the safest because we're in front of the red light before it turns, when the light is red, we are in front of the intersection, which is good. And this, when the light turns red, we're actually moving, and we're going to be moving into the intersection. So this is the non-safe method. So there you have it. That's one of many ways, of course, you could solve this problem. You could do it in a different order as well, but that's one method. Okay? And that's it for kinematics number 3.